2 minutes. 2 minutes.
No, we don't stop there anymore. Oh, we don't? It's not yet. It's not since no, that's me. Hey, look. I got recognized just like the Alpha Rec this yesterday. Alpha Rec? Yeah. Because I went in there to push up somebody. I was like, okay, let's go. Oh, yeah, I know you. So Alpha Rec.
Oh, outdoor rec. I thought you said alpha rec.
I'm Alpha Rec.
That's like a pretty bold statement, but alpha rec. That's you.
Would be true if I didn't get right.
Are you using the signal?
Not today.
I don't understand what you did. Like, we talked about last class, like all the, what all the things are and what they mean. I'm like, this would have been so helpful in any lab class we've ever had. Like, we've used it for so long, I never know what to do. I didn't go and study what it was called until the other day. Oh,
That makes sense.
yeah, that, I've seen it a lot before, I just never knew what it was.
What we got going on? Is it time? It's time. All right. 12:30. Let's get started. Lord, thank you for bringing us together this afternoon. Pray that you would help us finish the week strongly, that you would give us the energy and the will to finish all the things that we set out to do. In your name we pray. Amen. All right. All right. So, rewards are in order, right? I promise you guys. Yes. Ice cream sandwiches are how delivered. All right. If you're not here and you're on the Tuesday class, you'll get your ice cream sandwiches on this. They're not vegan, they're not gluten-free, they are regular plain old ice cream sandwiches. I understand that. You guys, if you feel comfortable eating them in class, eat them in class. If not, and you want to put it back in the bag, I can let you grab it after class. There's full packs in here. It'll be less melty than otherwise. All right. Now that I've cleared out my side of the bargain, right, we can keep going. Man, people just. All right, so what are we doing today? It looks like we've got a lot of stuff to do. Some of these are like 1 or 2 slides, so don't feel like it's crazy, right? So we'll start with recapping. Something happened where I accidentally put your guys' poll everywhere, and then the 945 classes poll everywhere. So this isn't what yours originally said. Yours was focused on block diagrams. We are going to clear this because I took a picture of it for that class because we need it for later. But you guys were focused on block diagrams, right? So what are we trying to do by creating block diagrams, right? What are we trying to do? We are trying to create a graphical representation of our equations, like of our model, that will show us how our different signals interact with one another. That is what we are trying to do, right? And we've said things like, right, so I think models was on there this morning. The models are the systems of equations that we've been developing, right? That's what they are. And so if we can make the model, hopefully then we can get it into a transfer function. And if we get the transfer functions, we can create block diagrams, right? This is not obviously apparent why this is useful yet, right? We're just kind of setting the stage for it. But once we get in like a couple of weeks, right? Once we get into a couple of weeks where we're talking about, when we do our MATLAB Simulink primer, right? And do some examples specifically with Simulink, we'll see why it's useful. Other than that, right, let's actually just try one, right? Let's do another one. I learned a cool trick. If I do this, then the toolbar goes away on the top of the screen. But it comes back all the time, even when I don't want it to. But anyway, so what do we got here, right? There's no problem statements. Dr. D never puts any problem statements with these problems. He just flashes a block diagram, and we're supposed to know what we're going to do, right? Okay. So here's a block diagram. What I want to do is I want to get a single transfer function for this entire system. That is what I want. I want one single transfer function for the entire system, right? I've got how many inputs here? Well, I've got f of s and g of s. And I've got two inputs and I've got one output, x of s, right? On top of that, I also want the individual transfer function for x with respect to f and x with respect to g. We'll talk about why we might want something like that. But you're going to see, I'm going to actually rename these as f of t, w of t, y of t, g of t, and x of t. So in general, if you see a capital letter, this is telling you that this variable has been translated into the Laplace domain already. Okay? Lowercase is typically time domain, capital is for Laplace, right? Obviously, there's the of t and the of s thing as well, but I'm going to do this in terms of a time domain transfer function since that's where we're at. So what do we have to do, right? We want one single transfer function, right? We get three things here, right? Three things that we want. I want the transfer function of x of t to f of t plus g of t, right? My total system-wide transfer function gives me the ratio of my output to all of my inputs, right? I also want the specific transfer function here and this specific transfer function. All right. These are the things that I'm, right? So how can I do that, right? We'll talk about it once we get there, but the process is going to be the same, right? Let's focus on part A first, then we'll talk about B and C. What's the why behind why would you want B or C? Well, I want to know just how my output responds due to a specific input, right? I know what that input F is, and I want to know how that changes my output specifically. I don't care how G changes it. I care how F changes it, right? Let's start this up, right? So I'm gonna color code these nodes here, right? So I've got this red node, I've got this green node, and I've got this blue node. So we're gonna do this. We'll start at the red node. Does it matter where you start? No. But I'm gonna start at the nodes, right? Why? Because I clearly know what is coming in and what is leaving, right? So if I start at that red node, I've got W of t coming out, and this is F of t minus, right? How do I know it's a minus? Well, I've got this minus sign here, right? Whatever else is coming in there, it's a minus. I'll track this back. It's going to be minus 4 times x of t, right? Minus 4 times x of t. Everybody sees where that comes from, right? And good? Okay. Let's move on to the green one, right? So what do we have entering the green node? Right, 7 times WT minus, right, again, minus 3 times X of T. And what does this equal? Right, what does this equal? Well, we don't have a name for that signal, right? We don't have a name for that signal, but, so right now, let's call it C. Right, we'll call this right here, if I can get my pen to work, which would be awesome if it did. Call this C of T for right now, right? C of T. Why C of T? Well, why not? I don't really have a good reason. I just picked C. So we're just going to call that something, right? And that's fine. And well, let's look at the blue node, right? Blue node's got a similar thing going on here. It's got a similar thing going on. I don't have a name for this signal in here. I'll call that D of T, right? Call that D of T. So I've got D of T coming out. I've got Y of T plus G of T, right? So let's talk about these C of T and D of T signals. Okay, let's talk about them. C of T comes out of that node and goes into an integrator block, right? Remember, 1 over S for us is the same as 1 over D, right? And these are integrators. So it comes out, and when it comes out, it's Y of T, right? If I take the integral of something and it gives me back out Y of T, what went in to the integrator block? Yeah, the derivative of Y, right? So instead of C sub T, right, I can write this as D times Y of T, right? Because D times Y of T times 1 over D gives me Y of T. Same deal down here, right? Some signal goes into my integrator, it comes out as X of T, so what went in there has to be D times X of T, right? Or the derivative of X with respect to T. Because remember, our D operator, capital D, is d dt, right? All right, well, we want the system-wide transfer function, right? When you hear system-wide transfer function, that means I want the ratio of my output to all of my inputs, right? What I'm trying to do is condense this into a single block that I can then use, right? To just give me my inputs and my outputs. Okay. So let's start with this dy of t equation, right? So I've got dy of t is equal to 7. Well, I'm going to plug in wt here. F of t minus 4 times x of t. Right? So all I did was I plugged in the red equation to the green one, and I think it's pretty clear where it went, right? That's all we're doing, okay? Because what is my goal here? My goal is to get everything in terms of f, x, and g. That's what I want. So I need everything in terms of f, x, and g. So I'm going to divide, well, before I divide everything, I'm going to expand that 7 times the quantity f of t minus 4x of t. Yeah, so I'll do that. And I'll do one last algebraic step here to get an equation for y of t. Right? Where I divide by d, and then I just negative 28 minus 3 is negative 30. Okay. So far, so good, right? Now I've got y of t. So what am I going to do with y of t? I'll plug it in here. Because once I get rid of that y of t, that equation will be everything that we need, right? It's going to be x of t, f of t, and g of t. Let's do that on the next slide. Right? I'm going to take that y of t equation and put it into the blue one, right? So the blue equation told me that dx of t is equal to y of t. Y of t was just 7 over d f of t minus 31 over d x of t plus g of t. Okay. And so we're going to do a bunch of algebra again, right? We're going to try to get all of our x's on one side and all of our inputs on one side, all of our outputs on the other. So I'll multiply through by d. All right, and I'm just going to move my x of t over after I multiply through. And I'll end up with this equation, right? And we know what to do with this now, right? Well, let's make it look a little nicer. Right?
Is there going to be a D on that too?
There is, thank you. Thank you. 100%. Question was, is there going to be a D on the G of T? The answer is yes, 100%. But you probably heard the second part, but not the first part. I'm really not used to having to repeat all questions for the viewers at home. So I'm trying to get better. I mean, this semester is just bringing me one step to my overall goal of being a game show host at some point, right? I mean, really, we're being honest. And Pat Sajak can't host Wheel forever, right? 3 more weeks. All right. So we end up with this, right? And if I want the over, remember, what did I say I wanted, right? For part A, I wanted x of t over f of t plus g of t, right? Remember, we've done this before where we keep our, we've been, but can you really do that here algebraically, right? Because it's not like you can just leave the 7 plus d over there, right? And just magically have f of t and g of t drop, right? So can you really do this? Not really. Not really. So why don't we do what we can do? Why don't I first just write an equation for x of t? I'm going to write this in a very specific way. I don't know why I put an x of t there. There's no x of t. All right, so I just solved this, and I left it as 2 parts. Okay. The total system response, right? X depends on both of these, right? So we can't just, it's not like when we did our load torque and our motor torque, right? Where we didn't have any coefficients in front and just kind of moved them, right? They were just added to each other, right? This is a little bit different because they're dynamically entwined, right? We need to handle this. So we can't really come up with one transfer function for the entire thing, right? But what we can do is come up with parts B and C, which is a transfer function for x with respect to f and one of x with respect to g. Well, how would you do that? I can't just isolate one of these, right? How do you just isolate one? Standard practice is to set one of them equal to 0 and then solve for the one that you want. So if you're looking for x of t over f of t, you set g of t equal to 0. You assume, we are assuming in this sense that the inputs, right? We're assuming that the inputs are independent. And then we can turn them on and off at will, right? So if we want to know just how our output is affected by the input f of t, we set g of t equal to 0. And there we go. This pen keeps running out of ink today. And we get this transfer function. Likewise, if I set f of t equal to 0, I'll get this transfer function, right? And if I wanted a new block diagram for this system, right? If I wanted a new block diagram for this system, how would I do it? I would do it in terms of that x of t equation that we have. Right? I know what x of t is. Notice that f of t, what I'm multiplying f of t by there, right? That's the f of t transfer function. What I'm multiplying g of t by there, that's the g of t transfer function, right? So you could sum these two signals together and you would get x of t. Right? That's what if you have to make a block diagram, right? So when is this going to be? I don't know. Also, start over. I don't know if any of you have looked at homework 4 yet. I posted it yesterday. Right? Homework 4 has a lot of stuff that you guys are gonna have to check with like MATLAB and Simulink, right? So do it by hand and then check it with MATLAB and Simulink and compare your results, right? And that's fine, right? When this is going to become most useful, the creating of block diagrams is going to be when you are doing Simulink, right? Otherwise, for what we're doing from a modeling perspective, they're nice tools to have, but they don't value add for us right now. They value add when you're modeling, right? When you're doing, like maybe in your senior projects, if you have some dynamic system that you want to model with a transfer function, right? You could do it that way. And Simulink and get an output. They're helpful when you're doing control systems, right? If you're running control systems that actually run through Simulink, right? All of these ideas come back again in control systems, right? Because you can write the transfer function for a controller that will have some effect on your dynamics as a whole, right? So these ideas come back in controls. We're not going to revisit them as such, right? Because controls is outside the scope of this course. But anybody has free time, which I don't know what that word means, but if you have it and you want to talk about control systems, then I guess come to office hours. I'm sure that you're all chomping at the bit for that one. I'm sure. Positive. All right. Do we have any questions on this? Right. So we can collapse again. Right. There's multiple block diagrams that are correct in many situations. Right. So how do we know if ours is correct? You can get the equation back out that you started with. There's a pretty good chance that you did it correctly for what you started with. What if you have to do one on an exam, right? And you totally mess up the model? Well, you can still have a correct block diagram based off of your model, right? So if you did the model correct, but you didn't do, or if you did the block diagram correct for whatever you started with, right? It's the same deal as if you messed up the free body diagram, but then you did the right model for the free body diagram that you drew, you still get the points, right? You still get the points. So in practice, right, for class stuff, if you have to do a block diagram, it'll be like what we had in the class the other day, where you're asked for where is a specific signal on your block diagram, and so if your block diagram doesn't show that signal, then you did the wrong one, right? That's kind of good. All right, you guys have any questions on block diagrams right now? If not, we can move. All right, I definitely changed these after you guys let me know that they weren't changed. So all the dates are correct in LabCloud now. Follow this timeline. The 11/8, homework 4, 11/15, rotational electromechanical system lab, homework 5, 11/22, and exam 2, 11/24. So the lab is going to be like last time. There's video online that you guys need to dissect to do it. You can pick whoever you want to work with again. That's fine. Doesn't have to be the same partners as last time. Right? If you want to vote someone off the island or take somebody back, take somebody else with you, then that's fine too. Okay. But yeah. There is one part of this lab that I haven't given you guys yet, and I will post that in LabCloud so that you guys can actually know what all the constants are. So when you make your model, it makes sense. All right, you guys have any questions on what's coming or anything like that? Okay. So let's talk about differential equations, right? So like this has been like a whirlwind tour of everybody's favorite things, right? We started with electrical circuits, right? Everybody loves circuits. And then we moved on to thermal fluids, and everybody loves that too. And now we're in differential equations, which is also another one, right? It's like engineering students' favorite thing, right? Look under your chair, you get a differential equation, and you get a differential equation. You all get differential equations. What's that? It does. I am Oprah in this analogy, 100%. Spreading joy through differential equations and other such things, right? So differential equations, what do we need to know? Well, hopefully this is more of a review than you learning, right? This is a whole semester's worth of class. I'm not going to go through a whole semester's worth of DiffEq in one day. But the things that we want to know are the things that we're going to talk about, right? So just imagine for a second that I have some nth order ordinary differential equation that is written in the form of an input-output equation. Okay? It has one dynamic variable and one input function, right? So it's single input, single output, right? And as an example, we're going to use this nice second order system, right? 2y double dot plus 12y dot plus 16y is equal to 3 u of t. U of t is some input function that we haven't defined yet, right? But we will, by the end of class, have defined a couple. If I want the total solution to any ordinary differential equation, I can break it up into the homogeneous and the particular solution. Okay? So y of h, y sub h, and y sub p. Right? The homogeneous solution is the natural solution. The unforced solution, right? The particular solution is the forced solution, right? And so in that vein, the homogeneous solution is where we were going to set the equation equal to 0. So we're going to say, imagine for a second that there are some natural dynamics that occur on this system. There's no input, right? I take this spring mass that's hanging from the ceiling and I pull it down and I let it go and I watch what happens, right? After I let it go, there's no input on it anymore, right? It's just going to go, right? That's my natural response. We're talking about natural dynamics of a system in this case, right? So the homogeneous solution, we set our equation equal to 0, right? And if we set our equation equal to 0, that's great. We're going to assume the solution form for the homogeneous, for the natural dynamics of an exponential. CE to the RT. Okay. Now, I want you guys to see this, right? If I settle on this as my assumed solution form, I can take the derivative of this twice. And I will plug it back in to my original differential equation, right? At the points indicated, right? So green goes to green, red goes to red, blue goes to blue. It makes sense, right? This is y of h. We're going to say that this is y of h, so that'll pop in there. And if we do that, we end up with something that looks like this, right? And for people at home who can't see my laser, yes, Jeremy, fire the laser, exactly. We end up with this, right? So I'm just substituting in y of h for y dot h for y dot, and y double dot h for y double dot. Right? That's all I'm doing. And I get this, and if I do some algebra, I'll get the form to the right, right? Where I can take 2r squared plus 12r plus 16, and I can factor out ce to the rt, right? And that's all equal to 0. Now, it's important to notice here that the only way that this equation can equal 0 is if the stuff inside the parentheses equals 0. See, the e to the rt term will never equal 0, right? It's an exponential growth or decay, depending on what r is, right? It's not going to equal 0. Now, we assume that at the limit as e goes, the e to the negative, right? We'll assume that a decay approaches 0, right? But it never actually reaches 0. It's asymptotic, right? So we're left with this, right? And that stuff inside that parentheses, right? The parenthetical terms there is a really important quantity for us. And this is the characteristic equation. Characteristic equation tells us something about the dynamics of the system. Right? Specifically, it tells us something about the solution form that we've chosen. Right? So if I have my characteristic equation, which is just a quadratic for second order systems, I can find the roots, right? I set it equal to 0 and I find the roots, right? And if I find the roots, right, that's going to give me some insight, as we'll find out later, into how I should expect this to behave. Okay, how do I find the roots? There are a couple of ways, right? There's three ways I suggest. The first, these are in no order of the way you should try. It's all personal preference. The first is quadratic formula for a quadratic equation, right? You use that and solve for the roots. The second is factor it. You totally factor this and get down, which is what happened here, right? Or you can use your fancy calculator to solve this equation for 0, right? And it'll punch out the roots for you. One of those things. On an exam, right, you're probably going to want to either get comfortable with having your calculator do this for you, or remembering what the quadratic formula is, right, or doing factoring, one of those. But if we do this and we factor it, we'll see that our roots are -2 and -4. And we're not going to say what that means just yet, but what happens is, because of our homogeneous solution form of c is e to the negative, or c is e to the rt, we can plug that in and we'll end up with two parts, right? Because each root is going to contribute something to this response, right? Each root contributes something. What does it contribute? Well, c1 e to the -2t and c2 e to the -4t. Right? So all we've done here, right, is we've solved for r, right? And if we go back, notice that our solution here, right, this solution, when I say the solution, I mean this, right? The homogeneous solution is ce to the rt, but we have two r's, so we need two terms, right? Two r's, we need two terms. We can solve for C1 and C2 if we have the initial conditions. For a second order differential equation, how many initial conditions do we need to solve for C1 and C2? or second order differential equation, how many initial conditions do I need to completely solve it? I've seen people holding up hands with fingers. Yeah, it's two. It's two, right? Why is it two? What's second order? Right? You would need 3 for a third order, 4 for fourth order, so on, so on, and so on. Need 1 for a first order. Okay. So if I solve this, right, with my 2 initial conditions here, I can get values for C1 and C2. It doesn't really matter what they are right now. So that's the homogeneous solution. We expect that the natural dynamics will be either an exponential growth or decay, right? And at some point, right, that response will either die out or everything will explode, right? Depending on whether you have growth or decay. The other half of this is the particular solution. Right? The other half of this is like the particular solution, right? And this is when we have a non-zero entity on the right-hand side. And typically, we call this our forcing function or our input. We talked a little bit last class about some different forcing functions, right? The common ones that we're going to use here, right? We've got step, ramp, ramp, step, pulse, impulse, right? We got a lot. We've got those are our general phrases, sinusoid, right? How do we determine the particular solution? We find it by guessing at the form of the solution. Well, guessing makes it sound like it's all up in the air, right? Well, they might be wrong. Well, you know what to expect out of your function if you know what you're putting in, right? For example, imagine that I had a sinusoidal input, right? Sine 4t. I know that I should expect some sinusoid out of that function. I don't know what it is, but I'll assume that it takes the form a sine 4t plus phi. What is that? Well, that's telling me that it's going to be a sine wave that has some amplitude, right? That's different than what it was originally. It's going to be scaled in some way, but it's also going to be shifted, and it's going to be running at 4 radians per second, right? It's still running at 4t. Whatever I put it in at, whatever the frequency that my sine wave comes in at, it has to come out at, but I can scale it and I can shift it in time. And that's what phi is. Phi is my phase shift. And we'll talk more about that in the last few weeks of the semester. But there's another way that we can talk about sine waves, right? And instead of calling it a phase shift, we can say that it's a combination of a sine and a cosine that happen at the same frequency, right? And it's the same idea, right? Because the phase shift is just going to move it. So if you had a constant input, right, you would expect a constant output. Hey, here's a table of things from a different textbook that's not your textbook. That's very useful because this is a common, this is the solution form of the first order differential equations and second orders based off of what the roots of the characteristic equation are. We'll come back to this again later here, but yeah. Let's do that. Just so it's nice and segmented so we can see what we're talking about. All right, so for first order differential equation, as long as you write it in this format where you have where you have a coefficient of 1 in front of the x dot term, then you can read off all those coefficients and just get what you need. And plug it right in there. That's going to be your first order differential equation solution. For second order, it depends what your roots are. And it can be broken down into distinct real roots. And we're going to talk more about this next week when we hit second order systems, right? And really dig into root responses and what we can expect and what it means for stability and instability in our systems, right? But in general, we have distinct real roots, which gives us this solution form. We've got repeated roots, which gives us the second solution form. Imaginary roots, well, imaginary roots mean if you imagine the imaginary roots. Poor choice of words. I've got this coordinate axis with real on the x and imaginary on the y. Imaginary roots only happen on the y-axis. They have a zero real component. Complex roots, which is the fourth one, will typically happen in complex conjugate pairs. We'll talk more about it next week when we actually get into second order systems and what this all means. Again, in terms of the system stability and the instability and all of that stuff. Okay? Okay. So cool, right? So let's do one. If you're given the following first order linear ordinary differential equation with an initial condition of y of 0 is equal to 3, determine the complete response. Okay. The complete response. All right, so the complete response is the homogeneous plus the particular solution, right? So let's start with the homogeneous solution here. I'm going to assume the solution form CE to the RT, right? Which means that y dot h is equal to RCE to the RT. And I'll plug that in here. So I'll get, well, I'm going to rewrite this a little bit. I'm going to write this as 4y dot plus 8 is equal, sorry, y dot plus 2y. Well, I'm going to rewrite this like this. I'm going to plug these things in for y and y dot, right? So I'll get 4 times the quantity y dot, which is RCE to the RT, plus 2 times CE to RT is equal to 6, right? We can do the same thing that we did before, where I factor out my CE to the RT. Sorry, this should be equal to 0 since we're doing, come on. It should be equal to 0, right? If my pen will work. We're doing the homogeneous response should be equal to 0. Okay, check it out. Great. I've got my characteristic equation here, right? Well, something that you may have noticed, maybe you didn't, because we've only done one so far, but I did the other one. Let's go back for a second. And we did this one. Right, hey, here's my characteristic equation. Right? Isn't that just, doesn't that look an awful lot like that? Yeah. Turns out we have the same thing, right? So your characteristic equation tends to be, right, whatever your y dot, right, 4r plus 8, which is just 4 times r plus 2. Right? In this case, r is equal to minus 2. So I know my root. So I know that my solution, my homogeneous solution, since this is first order, is just this, CE to the minus 2 times T, right? And I can evaluate this at my initial condition if I want. But I'm going to hold off. Right? We're going to hold on to this one as is. Right? I'm going to say that's the form of my homogeneous solution. I'll use my initial conditions at the very end, right, and solve for everything else. So how do we do the particular solution? Well, we need to assume a solution form, right? And what do we know? Well, let's write down our equation again. Remember, in this case, we're going to keep that input function, right? And our input is 6. 6 is a constant. So I'm going to assume that my solution takes the form of a constant. That I'm going to call lowercase a. So that's the solution form that I'm assuming that we're going to have. And if I take the derivative of that, right, since a is a constant, it's 0. So then I can plug it in, right, like we did before. Right, so I'll get 4 times 0 plus 8 times a is equal to 6. Well, didn't need a calculator for that one. 4 times 0 is 0. So I'm left with a is equal to 6 over 8, or, you know, if you prefer, 3/4, or if you're into decimals, right, 1/7. All right. So now we know a, right? And why is that important? Because we can say, well, yp of t is just equal to 3/4, right? Because our solution was a, the solution form we chose was a, so it's equal to 3/4, solid. So now we can put both halves of this together, right? And so we'll get y of t is equal to my homogeneous solution plus my particular solution. And I can evaluate this at my initial conditions. Right? So y of 0 is equal to 3. I plug in zeros for all of my t's. Hey, look, this one goes to 1, right? Because e to the 0 is just 1. So 3 is equal to c plus 3/4. A rough go for this pen today, man. C is equal to 2.25. So we can rewrite our equation. Y of t is equal to 2.25 e to the negative 2t plus 3/4. This is our solution. This is the long way of doing this. Not the wrong way, the long one. Long with an L. Okay, why? Why is this the long one? Well, you literally, before we started all of this, right before you started, you showed us a table that gives us the solution form that we need based off of the differential equation that we're given. So why didn't we just do that? It's a good question. Why didn't we? Because we need to remember how to do this. Okay? We need to remember how to do this. So let's check it with the table. All right, let's check this with the table. We ended up with y of t is equal to 2.25 e to the negative 2t plus 3/4. First, before we check this with the table, does anybody have any questions? All right, so I'm guessing no. Then. All right. So let's go back to our table. Oh, please don't. Here it is. If I go back to my table, I'm going to get rid of this up here so we can work a little bit. My equation originally was 4y dot plus 8y is equal to 6, right? Notice there's some caveats here. A cannot be equal to 0, right? That's the caveat on this one. But also, look, this is not in the right form, right? My original equation is not in the same form as the one in this table. So don't just start plugging things in because it won't come out the same, right? We need to divide through by 4 first. Instead of 6 over 4, I'll put 3 halves. 3 halves. All right, okay. So now, can I build my solution based off of this? Not if my pen dies. So y of t is equal to b over a. Well, 3 over 2 divided by 2, well, that's just 3/4, right? Plus c, e, well, 2, a is 2. Okay. Look at that. Then I can use my initial condition to solve for what c is, right? And use my initial conditions to solve for c. So yeah, table works. Right? Yeah, the table works. The table already. Yes.
So this is a general solution.
Right.
So for
The question was, that's just the general solution for.
I've never seen this before.
Yeah.
I was just looking because we got off the curriculum.
Yeah. So with this, right, the table shows you a general solution, and then based on the equation that you have, you can fill in the blanks. It saves time. Now, I will say this. There will come a time in the near future where you are asked to solve these things using, specifically asked to use the Laplace transform method to solve these. And some of you will inevitably say, that's okay, I'll just use the differential equations method of solving these things. And then you will get 0 points because the instructions told you to specifically use the Laplace transform method. So the moral of the story is if you're told to do something specifically, do that specific thing. Okay? Is that real world? Is your boss ever going to come and say, oh, you didn't use Laplace transforms, get out of here? No, it's not. But this is a school and not everything translates to the real world, and I have to test whether or not you can do Laplace transforms. So that's in the syllabus. You should be able to check your answer. You will definitely get the right answer. And on top of that, this should help inform you what your answer should look like, right? Because whether you do it in Laplace or time domain, you should get the same answer out, right? It just should be how it works. All right, let's try another one. This time it's second order. Woo! Second order. Given the following second order linear ordinary differential equation with initial conditions y of 0 is equal to 2 and y dot of 0 is equal to -1, determine the complete / total solution or response. Interesting. Let's see what we can do, right? So once again, right? So this time I'm going to take a shortcut, right? Because we've done this a couple times and I think we've proven it out. That if you need the characteristic equation, right? If I need the characteristic equation, do I have to go through and do the whole thing again? No, don't. If you don't, I can rewrite this as this. This is the characteristic equation, right? There it is, right there, said and done. If you don't believe me, that's fine. It's still true, right? But you can prove it. You can go back and you can do the homogeneous solution, right? Remember that we choose y sub h is equal to ce to the rt, and you can take the derivative of that twice. You can plug it into the equation. You can factor out the ce to the rt's, and you know what you'll be left with? 2r squared plus 8r plus 6. That's what you'll be left with. I can find the roots of this, right? I can find the roots of this because this is just going to transform into this, right? And so my roots end up being -1, R1, and R2 is equal to -3. So I've got distinct real roots. All right, so I know what solution form I should expect if I look at the table, but we're not going to look at the table. We're not going to look at the table. So since we know our solution form for a homogeneous is this, we'll end up with ce to the -t plus c2e to the -3. I'm going to leave this as my homogeneous solution for now, right? We'll apply our initial conditions later, but for now, this is where we leave it, right? And we're going to move on to the particular solution. Now, this has a sine wave going in, right? So we've got a sinusoid input, which means we should expect a sine wave out, right? And we're not going to treat it as the sine of omega t plus phi. We're actually going to treat it, we're going to choose a particular solution form. Might be dead. We have a little bit of life. Ah. Yeah. It'll work. Last year, the pen was broken for like 2 weeks straight. I emailed tech support, the help desk, every day for 2 weeks before they came and gave us a new pen. It was awesome. I had to do everything on the whiteboard. It was great. I don't know how we're going to do that in this modality. If I have to, I'll have to bring a tripod in and move the camera to the front of the room, and we'd have to do that. Can be done. It's not ideal. We'll get it fixed. Okay, neither here nor there, right? So particular solution. I'm going to assume the solution form of A sine 4t plus B cosine 4t. Well, why aren't you going to use that capital A times the sine of omega t plus phi? We could, and in fact, this is the same thing. This is the same thing, right? Why? Why is it the same thing? Well, all this is going to do is it's going to take my sine wave, right? It's going to scale it, and then it's going to shift it by some cosine that's also going to scale, right? So it's just taking my sine wave that I put in, and it's scaling it, either shrinking it or enlarging it, right? It's either amplifying it or attenuating it. And then it's shifting it in time, right? So it's going to give it some phase shift. It's the same equation. It's just in terms of sine and cosine instead of omega t plus phi, right? Why? Why not do omega t plus phi? I don't feel like explaining phase shift right now to everybody, and we're going to talk about it after exam 2. Also, it's easier to take the derivatives of these because we're going to have to take the derivatives of these twice, and taking the derivative of sine and cosine as a function of one thing is easier than of two things that are changing with time. So let's take the derivative. We get 4a cosine 4t minus 4b sine of 4t take the other one, double dots, 16. Should be the same. I'll get there. Okay. All right. So that's fun. We can do that. Not a big deal. The real fun part now is that I've got to take those equations and plug them back into the original equation for my y double dot and all that stuff, right? So again, remember those go in those spots, right? So let's get to it, right? It should be, okay. So remember, the important thing to remember when we're dealing with this is, right, we know that the input frequency has to be maintained. So if we're at 4 radians per second to start with, we know we have to come out at 4 radians per second. That's how it works. What does change is the scaling. And what changes is how big is my sine wave and do I have any phase shift? So we're left with this, right? And this is gross to look at, right? Glad we all agree on that. But we can do some stuff, right? And so what we're going to do is we're going to treat the cosine terms and the sine terms like vectors. How do I mean? Well, you know how like in statics and dynamics where you had a force vector that was two-dimensional, so it had an I and a J component, and then you could like group all the I's together and all the J's together. We're doing the same thing, but with the coefficients of sine and cosine. Right. So all of my cosine 4t terms, right? I've got negative 32b plus 32a plus 6b is equal to 0, right? Why is it equal to 0? Because I have 0 cosine 4t as in my input, right? There's no cosine portion on my input, so it's 0. And do the same thing to the coefficients of my sine terms. Negative 32a minus 32b plus 6a is equal to 10. Right? So is this really like a vector decomposition? No. Right? What it's really doing is I'm saying that I know that all of the sine terms, eventually the coefficients of all those sine terms have to equal 10. Right? And I know that the cosine term, the input of the cosine term is 0, so the coefficients all have to add to 0. So we can solve this, right? Two equations, two unknowns, solve it simultaneously. No, thank you. So we get this. We then take that A and B, and I'm going to put a box around this equation, right? Because remember, this is the form of my solution that I said it takes, right? B box. So I'm going to plug A and B into that equation, right? Now I have the particular portion and the homogeneous portion. I'm going to put them together. I'm going to use my initial condition and I'm going to solve. Use my initial condition and I'm going to solve for C1 and C2, and then I'll have the whole thing. It'll be glorious. So the total solution is just the homogeneous solution plus the particular solution, which is C1 e to the minus t plus C2 e to the minus 3t minus 0.1529 sine 4t minus 0.1882 cosine 4t. Just so we have them here, I know that this is 2. Right, so I have my initial conditions up there. I'm just keeping track of what I see. That's great. But I have 2 unknowns, so I need another equation to find C2, right? Lovely. Guess I've got to take the derivative of this equation. How would you know to do that if you hadn't taken differential equations? Well, the initial conditions are equated, right? I have one initial condition for y and one for y dot. So if I want to use both of these initial conditions, I need to have one equation for both, right? Plus, taking derivatives is fun, right? Everybody loves taking derivatives. They're the best. So I gotta switch that to cosine. My bad. Okay. So there we are, right? We've got the derivatives. It's not too bad, right? We just have to remember the rules for taking derivatives of exponentials and sinusoids. Not too bad. So now we evaluate this, right? We'll evaluate the first one. So y of 0 is equal to 2 is equal to C1. Well, e to the negative 0 is 1 plus C2. E to the 0 is 1. So the e's go away here, right? Sine of 0 is 0, right? Cosine of 0 is 1. So I end up with this, right? Just plugging in 0 for my t. So that's simplified down really nicely. The next one will simplify down pretty nicely too, right? Because we know that y dot of 0 is equal to negative 1. Well, that's going to be negative C1 minus 3 C2. So, okay. Because cosine of 0 is 1 and sine of 0 is 0. Hey. You can solve these simultaneously. And we'll plug it back into our y of t equation. And that's it. If you put this into the table that we just used, well, you get the same answer out. It's going to look good. It looks slightly good. That's fine. If you wanted to, right, you could plug in your initial conditions and see if it comes out what it should. It will. Is there any questions? Again, I'm hoping that this is more of a refresher than like I just totally forgot how to do all of this. If you have major issues with differentials, come to office hours, right? We can hopefully get you straightened. But hopefully. No questions though? Everybody's all right? Okay. Okay. Yeah. All right, so if there's no more questions, let's talk about what we call the complete response. The complete response. Well, we talked about the total response. And it's slightly different terminology, right? In the total response, we've said that the total response of a system is the homogeneous plus the particular solution, right? Which is fine and gives you the natural plus the forced responses. But in terms of what our system looks like, what the response looks like, we can break this up into two different phases, right? We can break this up into the transient response and the steady state response, right? And sometimes, depending on the system, it may be more advantageous for you to talk about it in terms of transients versus steady state. Well, what is transients? What is the transient response? It's the part of the response that decays as time goes to infinity. Now, this is a specific definition for a stable system. If you have an unstable system, you won't decay as time goes to infinity, but you also won't reach steady state ever, right? So this is predicated on you having something that is stable to begin with. Right? So the transient response is the part that dies out as time goes to infinity. And the steady state response is everything that's left over, right? It sticks around as time goes to infinity. You can see in our plot here, right? It's very clearly labeled. Steady state response is the right-hand side, right? And the transient response is on the left-hand side, right? So another way of thinking of it is that something that's transient changes with time, whereas steady state is what? Well, it's steady, right? It's constant, it's there. Okay. Do you have any questions on the complete response? And so instead of talking about this as homogeneous and particular, you can talk about it as transient and steady state. And sometimes when you do your differential equations, you will get pieces of your steady state response from your homogeneous response, and sometimes you can mix and match. They can happen in either the particular or the homogeneous. So there is a distinction between the two and how we would write those equations, right? But it's important for us. What's important for us is to be able to designate which part of our response is transient and which part is steady, right? That's what's important. So we've talked about characteristic roots. Now, is it possible? Do you guys think that it's possible that the stuff we've been talking about with transfer functions is somehow related to the stuff we've been doing with differential equations, and in fact that the characteristic roots are somehow related to the transfer function? You guys think that that's possible? Somewhere written up there that it's possible. Right? So the answer is yes. Turns out that if you have the transfer function, you can figure out what the characteristic equation is, and therefore what the characteristic roots are. The characteristic equation is the denominator of my transfer function. Remember the example we did at the beginning of class, right? We have those two transfer functions, right? They both have the same denominator, right? That's because they both have the same characteristic equation of the system. The roots of the characteristic equation are referred to as the poles of the system. The roots of the numerator of the transfer function are referred to as the zeros. We will talk about those a little bit more in this class, but we're not going to really get into what they mean beyond the fact that you can figure out what the system's poles and zeros are. They come into play when we talk about control systems, and they're very important in determining how we design a control system, but we're not going to play around with them too much here. So let's do this. Determine the characteristic equation and the roots. And find the transfer function poles and zeros. Just worry about the poles, don't worry about the zeros. All right, so what's the characteristic equation for this? Who wants to volunteer a characteristic equation here? Say one more time. The previous one was the R squared equation. What do you guys think? What's the characteristic equation for this system? Can you tell just by looking at it? If you can't tell just by looking at it, that's fine, right? How can we get it? Well, find the homogeneous response, right? How do you find the homogeneous response with CE to the RT? Right? Do that one too. Yes, got it. 0.04 R squared is 16R per 7,000. Right? That's the characteristic equation. And if you took the roots of that, you would get our very first complex conjugate root pairing. It's exciting to, very exciting. What does that mean? We're not going to talk about what that means today. We'll talk about that next week. There's a whole lecture where we talk about root responses, and everybody looks at me very excitedly. And by that, I mean like half asleep and wishing that I would stop talking about, wishing that I wouldn't talk about root responses for 2.5 hours. Right? That's what I mean. But super, super good. All right, so we have, how would you know that that's a complex conjugate? What does that mean? Well, it's got a real and an imaginary part. We're going to use J as the imaginary number here instead of I. And that's something that is, it's an electrical engineering thing that got brought over to mechanical engineering because of control systems. Right? All right. So we got some real and some imaginary part, right? Remember that just means we have the square root of a negative number, square root of -1 in there, great. That's all it's telling us. So how do we find the transfer function poles and zeros? Whoa. Whoa. Well, let's find the transfer function, right? What's my transfer function? Oh, that's not the right button. Shut it down. All right. How do I get my transfer function here? Right? We're going to do a time domain transfer function. What do we do? First step. We insert our D operator. Right. Oh my gosh. I can't believe it. Right? He said it before that the transfer function denominator was the characteristic equation, but I didn't believe it. But now that I see it, I still don't believe it. The truth, man. Truth. What are the roots? What's the poles? Right? The poles of the system are the roots of the character. I can't say characteristics today. It was like bad, man. But anyway, right? The same characteristic equation. Why is that significant, right? Well, it's because the characteristic equation tells us the natural dynamics of our system, and this is something that is inherent to our transfer function, right? So our transfer functions capture the natural dynamics of our system, right? Which is nice. Nice to know. But you guys have any questions on characteristic equations from transfer functions or what all that means, right? We okay with that? We're bouncing a couple of different topics around, but I promise it'll all come together today. All these things that we're talking about. Well, maybe not the transfer function thing, but the rest of it will jive. The rest of it will jive. So we can talk about DC gain. So DC gain is a pretty powerful analysis tool. What it allows us to do is if a system is subject to a steady or a constant input, then we can determine what the steady state output is from looking at our equations without having to do a heavy analysis. We'll do it very quickly. It comes from DC circuit, right? It comes from DC circuit analysis, right? Because it's not alternating, it's a direct current. All right, by definition, the system DC gain is the steady state gain to a constant input. For the case when the output has a constant value at steady state. What would that be? That would be like a ramp and hold, right? Or a step. The DC gain for a given transfer function is computed by simply setting S equal to 0. But in our case, since we're not using S yet, we're setting D equal to 0. Right? Now, what is D? We talked about it earlier. What is D? What does D signify? D over dt, right? If we're setting that equal to 0, what does that mean for us? Well, that means that whatever we're looking at is not changing with time anymore, right? At steady state, is our system changing as a function of time? No, it's steady. Steady implies that it's not changing, right? Steady, just like my hand, right? So what we're doing is we're setting all of our differential terms to 0 at steady state because nothing is changing with time at steady state. right? And this allows us to get the DC gain. So what do I mean by this, right? So hey, check this out. We've got this block diagram, okay? Everybody's new favorite block diagrams, right? They're the best. Right? I'll make these D's here because why not? Do this one better. Okay. Okay, so what is it showing? It's saying that I've got some input voltage of 2 volts. That goes into my solenoid, right? That comes out as an electromagnetic force, which goes into my spool valve, which comes out as some position. Well, okay. So let me ask you guys this. If I take this first, if I wanted the DC gain of this, what is it? What is the DC gain of this transfer function? What's the DC gain of this transfer? How do we find the DC gain? Just talked about it like a slide ago. Set D equal to 0. What happens if I set D equal to 0 here? Yeah, what am I left with? Really? If you set D equal to 0? 12 over 1.5. Some people call that 8 if they can write with a pen, which I cannot. That's my DC gain. So at steady state, what this is saying is that at steady state, the dynamics here are no longer transient, right? We get rid of the part that is changing as a function of time. What we are left with is now this gain block, right? We're left with this gain block. What do we have coming into that gain block? I've got E in, right? But I know that E in is 2 volts. What comes out? FEM steady state, right? The steady state electromagnetic force comes out, and then what comes out of here? My steady state position. Okay, let's try this one, right? What's the DC gain for this block here? What's the DC gain here? Heard it. Yep, 1 over 7,000. That seems like a lot. I mean, I'm pretty sure that everybody here knows without reading a calculator. That's just 1.43 times 10 to the minus. Everybody knows it. It's not even great mentioning that. I know. But, yeah, if you're into decimals, or if you're into decimals over fractions, then, you know, reconsider it. Fractions are better. What? Yeah. So now at the top, we have a block diagram that is good just for steady state. So at steady state, let me ask you this. What is my electromagnetic force at steady state? Based off that block diagram. Whoa, 55,939. Man, no. No. All right, so I've got 2 volts coming in to a gain block of 8. What's coming out? Just look at the top one. Heard it. 16. It's 16 newtons. You got 16 newtons, man. What is my Y steady state? I've got 16 newtons going into my gain block of 1 over 7,000. What's Y steady state? Sure. 0.00229 meters, or 2.3 millimeters. 7,000, right? Obviously, that's 7,000. Right, so here's another question. What if I didn't care about, I just wanted the total DC gain for the entire system? What would it be? How would you find that? Yes, Trevor. Exactly. Do this. Yeah, you would just multiply them together. So the total DC gain for the whole system is just 8 over 7,000, right? Let's see if that works. Right, so we know that my Y steady state should be 16 over 7,000, right? Well, if I had this whole thing as one block diagram with a DC gain of 8 over 7,000, and I have 2 volts coming in, that means that what's coming out is 16 over 7,000. So yeah, right? We have 2 blocks in series. We just multiply. This becomes very nice for us if we're talking about steady state dynamics of a system, right? Because now, instead of having these transient portions, everything is just an amplification of a signal in something, right? This is going to be really helpful when we start trying to draw responses to systems by hand, and we need to figure out what are my steady state values, right? Where do I expect this system to be at steady state? Right? That's where this is going to be really useful. Do you guys have any questions on DC gain? All right, so again, if you hear DC gain, if you're asked for the DC gain, you're just being asked for the steady state gain of the system, right? That's the big takeaway, right? Don't make it, don't confuse it as it has to, don't think that it has to be an electrical systems thing, right? It's just, what is my steady state gain for the system? That is the DC gain. Set your S's or your G's equal to 0 and figure it out. Yeah, awesome. Oh, sorry, say that one more time. So the question was, are we going to link the steady state conditions to the initial conditions? And at some point, yes. But you'll see it's more of a way that we can, so the initial conditions don't affect steady state, but they affect the entirety of the response, right? So steady state will be whatever it's going to be, but where you start depends on what your curve is going to look like. It's a good question. We'll talk about that actually in a little bit, because we're going to get into first order system response here. We are cruising. All right. So I'd like you to recall the events of the past few weeks, right? And we have done lots of modeling, and we have actually modeled quite a few first order differential equation systems, right? These are systems that typically look like mass damper systems, RL or RC circuits, single chamber hydraulic systems, single pressure vessel pneumatic systems, or single capacitance thermal systems. Right? So we've done a lot of these, and we've done state space, so we've had series of first order differential equations that we've been messing with. And it turns out that most of them look like this, right? So here are some examples of ones that we've done. I mean, we haven't done the pneumatic one, but this is what they would look like. This assumes that we have a laminar flow to our valve. This one's a laminar. And so I've got a first order mechanical rotor. Right? We've seen that. We've seen that one. We've seen the RL circuit. We haven't done many RC circuits, but I don't think it's a stretch that you guys would think that the equation will look pretty similar between an RL and an RC circuit. We've got first order pneumatic chamber that assumes a laminar valve flow, which means it's a very low speed gas. And we've got first order thermal chambers, right? And we've done hydraulic systems, right? We did that one on the homework. That was 2 first order hydraulic systems, right? And we were filling the tanks. All of these have something in common. And we're going to start talking about these first order systems in terms of their standard form. The standard form says that tau, y dot, plus y is equal to A times some input function, u of t. A is just some function. So tau and the dynamic variable y are defined in this table for each of the systems that we just looked at, right? And so for the mechanical rotor with a dynamic variable of omega, we've got our tau as J over B. In all the other cases, it's R times C. Right? I'm going to go back to this. Remember, tau y dot plus y is equal to A times U of t. Right? Let's use the mechanical one as our example. Mechanical is not in the appropriate form for us, right? We need a coefficient of 1 in front of our dynamic variable. So I have to divide by b here to get this in the standard form. If I want this in the standard form, it's J over B, omega dot, plus omega is equal to 1 over B. My input variable is going to be whatever that input temperature happens to be, right? That temperature is a function of time. Is it a step? Is it a ramp? I don't know, right? But it's something, some function of time. Yeah, Trevor. Sorry, right. I don't know why I said temperature. I saw a T. That's what my brain went. My bad. It's torque. But that torque is a function of time, right? That torque can be a step, it can be a ramp, it can be a constant, right? It can be whatever it has to be. Sine wave. But maybe this describes a machine that gives wicked Indian burns, right? So it's a sinusoidal torque. It goes back and forth and back and forth. But the point is, when we have standard form, right, that y variable has to have a coefficient of 1. Otherwise, you don't have it in standard form. Why is it important? Well, it's important because of tau. It's important because of tau. What is tau? What is tau? You guys have probably seen tau before in physics and circuits and probably instrumentation, I guess. Right? But it has to do with, so what is tau? So let's talk about the homogeneous response to a first order system, or the natural response. We'll talk about the natural response and we'll talk about the forced response and how they work together, how we get to our standard form of phase together. But in our standard form, we've got tau y dot plus y is equal to 0. Right? Because we're talking about the homogeneous response, so we have 0 input. I can find the characteristic roots of my equation here, right? As I create my characteristic equation, turns out that the root is going to be -1 over tau. Right? -1 over tau. There's only one characteristic root because it's a first order differential equation, right? And so because it's first order, we only get one root. So we can write our homogeneous solution, right? And we get C e to the -t over tau. Turns out that when we have a homogeneous solution, right, the constant C is simply just equal to whatever my initial condition is. Right? We'll call that Y naught right now. Right? Right, so if you plugged in 0 there, right, you would get C times 1 is equal to Y naught, so Y naught is equal to C, right? That's all we're saying. All right, so that's the homogeneous solution, and in order to talk about the complete solution, we also need the particular solution, right? Well, let's talk about this. That's just the solution we came up with for our natural solution, right? For our homogeneous solution. The constant tau must have the units of time. Because we need to have a non-dimensional exponent. And so we call this the time constant. Tau is the time constant. What is the time constant? Well, for a first order system, our time constant has the following characteristics. First, it's an exponential rise or decay to a 0 steady state value. And so it's going to die out. When t is equal to tau, right? So when one time constant has elapsed, the natural response of my system has decayed by 36.8%. It's just e to the -1. When 4 time constants have elapsed, 4 tau, we consider this to mean that our entire response has died out. The transient response is gone. Really, it's 0.02, right? So 2% of the original response, which is small. If you go to 5 time constants, you don't get that much more bang for your buck. You leave it at 4. Okay. So we define the settling time of our system, or the time that it takes for us to reach steady state, as 4 time constants. So T sub S, settling time, is equal to 4 tau. Okay. Equal to 4 tau. So that's the natural part of our response, right? That's a big idea. It's not immediately apparent why it's a big idea yet. But the idea of the time constant is going to be really nice for us because, as we're about to see, when we try to draw some of these responses, and we're trying to understand how a system is going to respond to a specific input, understanding how long it takes for it to get to steady state is a big part of that, right? And it's often one of the ways that we compare multiple systems together, right? Systems that do the same thing. Like how long does it take you to get up to operating speed, right? How long? That's steady state. How long does it take you? Right? It's a performance measure for our systems. You guys have any questions on time constant? Turns out for a first order system, there's 2 things that we need to know to characterize the response completely. It's time constant and steady state. What's my steady state value? Those are the two things that are most important. The two things that are most important. So how do we have, what does a first order system look like when it responds to a step input? All right, so now this is the part where we are going to say, we know what the homogeneous solution is. I know the natural dynamics already, right? We came up with that just a minute ago. Now I need the particular solution for a step input. What does that look like? Well, suppose that the input u of t is equal to u, which is just some generic step input, right? But a step input has a constant output, right? Because it hits a level of state. Right? So you would expect that your input or your output should ramp up and stay at some level, right? This is going to have a constant input. All right, if it's a constant input, we learned it a little bit just a minute ago about an analysis tool that would help us determine the gain of the system when we have a constant input, right? Well, let's keep going. So I already know the natural response, right? I can construct my entire equation here, right? And I can put it in standard form. Turns out that for the particular solution, if we're just worried about, if we're just looking at steady state, right? All of my differential terms go away, right? My y dots turn into zeros, so I'm left with y is equal to AU, which is just my steady state response. Right? Okay, so for a step input, my particular solution for a step input is just my steady state response. Okay. So you can combine these two things to get the total response, right? You got CE to the negative T over tau plus Y steady state. That looks a lot like the equation that came out of that table, right? Looks a lot like the first line of that table that I showed earlier. The next thing we have to do is we have to apply our initial conditions to solve for C, right? We take this, we apply our initial conditions, right? So y of 0 is going to equal some y naught. Okay, so we'll go through the motions here, right? So I've got y of 0 is equal to c e to the 0 plus y steady state is equal to y naught. So c is equal to my steady state, or is equal to my initial condition minus steady state, e to the negative t over tau plus y steady. And notice, now this solution is set up as a transient response versus a steady state response. This is my complete solution. So it turns out that my system response for a first order system to a step input depends on the initial condition and the steady state, right? Specifically the difference between my initial condition and steady state, the time constant and steady state, right? So can we draw this by hand? Sure we can. Totally. We can totally draw this by hand. How do we do this? Well, there's a few steps, right? So here's my rules for drawing first order response by hand. And these really go for every type of response. It's not just to a step input, right? These things will work for you. So first, we write the equation in the standard form and find tau, right? We need to find the time constant. So rewrite this in the standard form and find tau. Then find the settling time, right? Which is 4 times tau. Then find your steady state response. for a constant input. Then you're going to sketch an exponential response from the initial condition to the steady state value. If your initial condition is larger than where steady state is, then you're going to decay down to it. If it's smaller than where steady state is, then you're going to grow up to it. And our response will approximately reach steady state at the 7. Okay. 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 So let's try. We got some time. We burnt, we burnt through this stuff there. I want you guys to take a few minutes, I want to say take 15 minutes and determine, 20 minutes, I need 20 minutes, determine and draw the response. Do it on your own, and then we'll talk about it. Take 20 minutes. Oh, sorry. There's one thing that's not on here that you guys should know. EN is equal to 2 volts. That'll be helpful probably. Come on, let's go. One more. Yeah, assume that the initial condition for the force is zero. Okay. Good question. All right, 2 more minutes, everybody. guys. In 20 minutes. What we got? What do we do? How do we do? Really hoping that you guys want to do this, you know, you don't know what I'm doing. I've said that before, and then I've gotten end of course surveys where they say professor claims he doesn't know what he's doing and he's learning it at the same time as us. So, I mean, that's a joke that I guess doesn't hit with a lot of people. So I do know what I'm doing, promise. Anyway, what do we need to do? Step one, put this in the standard form. Right, it's not in standard form yet. Right, standard form tells us that tau times y dot plus y is equal to a times u of t. Right. Let's unfreeze. If I want this in standard form, I have to divide everything by 1.5. Right? I get everything to 1.5. The nice thing about standard form is that I know exactly what tau is immediately, right? Which is the point. Right? My time constant is just right here. Right? It's right up front. Because I know what tau is, finding the settling time is also really easy, right? It's just 4 times my time constant, or 8 milliseconds, 0.008. Okay. My steady state force, what is that? Well, if you take this equation, right, which is in standard form, we'll do it out. Right? We've got this. At steady state, this is going away. So I'll have F steady state is equal to 8 times the steady state value of my input, which is 2, which is just 16. That's where the 8 times 2 comes. Now we have to get to the drawing. The drawing can be tricky. And then I will show you a plot from Simulink that will prove that the drawing is pretty good. Well, not my in particular drawing. It won't be very good. You'll see it. It will struggle hard to be good, but we'll do what we can. Okay, so we're going to draw this, right? So Dr. D said that the only things that we need in order to draw this, right, are settling time. I'm going to have time in milliseconds on the x. I'm going to have force in newtons on the y. Dr. D said all we need is settling time and steady state. Right? That's all that we really need. True, I did say that. Right, so I'm going to bring this out to 12 milliseconds. And up to 16. So what do I know? Well, first off, I'm going to make a line here. This is my steady state force, right? If I know tau, then I know my settling time, right? My settling time we calculated was 8 milliseconds. Everything beyond 8 milliseconds is considered steady state. Everything before depends on where my initial condition is. I'm assuming that I'm starting from rest, right? It's not explicitly stated anywhere, and I apologize for not saying that, but we are starting from rest. If we're starting from rest, we'll be starting at 0 force, right? And we're going to have an exponential curve all the way up to our steady state. Man, I actually did good on that one. Last class was a struggle. I could not get that to go. Could not get it to connect. They're on different levels. I'm happy with that one. I'm not even going to post the other lecture. I'm just going to post this one because this picture is so good. Okay. So that's the drawing. That is the first order system response for this system. What if we started at a force of 18, right? Because for some reason we did. Well, then it would drop down. It would be an exponential decay down to 16. Doesn't really make sense for force, right? But for position, something like that would make more sense. So I said that, let's stop sharing this screen for a second. Let's, I ran the model in Simulink. Okay. I ran the model in Simulink. And this is what I got. It looks a lot like the curve that we just drew. Right? It's close. It's not exact. Right? It's not exact. This is going to be better. Right? Why is it going to be better? Because it actually does the differential equations. It doesn't just estimate everything. Right? It actually does the math. Are we going to be able to pull off anything meaningful from our hand-drawn graphs? I would say that if you needed to use this for analysis, you should use MATLAB or some other software package that will graph this for you accurately, right? However, it will get us in the ballpark, right? Remember, all of the models that we are doing in this class are linearized, simplified versions of real-world systems, right? And because of that, there are inherent errors in them. Right? They're not complete models. But the game is how do we balance model complexity and cost? That's the game. You guys have any questions on, is there any questions on drawing first order responses for step response? Do you have any questions on anything we did today? I did it in Simulink, but there is also a step function. So we'll learn about this. There's a couple ways that we can do all these things. MATLAB has built-in step functions that will do it for you. I use Simulink just because it's a little bit, I find it to be a little bit faster in terms of building the transfer function. It's not hard to build a transfer function in MATLAB. 6 of one, half dozen of the other. Right? But yeah, you can. We'll talk all about that. All right. We are going to save this next one until next week. First order system to a point. Okay. We'll save that till next week. We are going to tie this up though because I did promise, aside from ice cream sandwiches, I promised that I would finish, we'd pick up our story, right? So you guys got the good ending because you got the good average, right? So your story is going to be different than the story that the other class got. Right? All right, so Professor Q stopped in his tracks. Tell me everything she said to you, be as specific as you can. You start telling Professor Q about your day, you tell Professor Q everything the code told you, but you had a feeling that you should leave out the whole instrument of my vengeance stuff. Then, when I was walking away, she yelled, 3 witches you shall meet upon the road to your fate. First is twilight, the second is night, third is the coming of death. Is that everything? Yes, he responded. Well, that was a pretty crazy morning you had. Sounds like you were right, though. Just a crazy homeless lady. What are you waiting around for? You better get started on your exam. Yeah. You took your exam, you think you did pretty well. As you left the building, you stopped to think about just how weird your day had been, especially the part where you had to recap everything to Professor Q. You needed to get something to eat, but not until after you showered and got the chrome dust off. You shower, head out to get some grub. Time to get my eat on, you think? As you walk towards Love's Way, you can't help but feel like you're being watched. Will be continued in exam 2, the mother. Huh? All right, so today's deep thought for your, if it will let me, no, apparently, no. Okay. Well, apparently it doesn't want to play ball right now. We all know that the moon isn't made of cheese, but if it were made of spare ribs, would you eat it? Would you? Last class said yes. Pretty resoundingly. Is it letting you guys it's not. Hold on. Please hold. Please hold. I'll get us. I'll get there. I know how to do this. Um, hold on. Stop telling me tutorials. I don't need tutorials. Okay. Wait for it. It's going to happen. There. All right. There. Now everybody should have it. There we go. Man, space. Everybody's digging these space rooms, man. Space rooms. Good to know. All right. You got a couple more, and then you guys can go. Yeah. Okay. How's everybody feeling? Okay. And last one. With that. Okay. Hold on. Too long class. This is the All right. Have a good weekend. If I don't see you, I have office hours from 2 to 5 tomorrow. Right.